electromagnetic induction. You come across this term induction. First of all, while dealing with electrostatics, they have used the term electrostatic induction. The entire detailed study of capacitors is based on that electrostatic induction. Here it is electromagnetic induction, EMI, normally known as. Before we study electromagnetic induction, let's study about this change in flux. Flux, is represented by the letter phi, delta phi. You already know flux, magnetic flux is given by B A cos theta, or in vector form you might write B vector B dot vector A. Now you see flux is depending on three things: B field, A area, and what's theta, angle between magnetic field and the surface area vector. Now if you want to change flux, you have three ways. You might change only B, you might change only A, or you might change theta. Then you could use changes in 2, and that way it will be wider process. But let's study these three dependence in detail. You see only magnetic field is changing. In that case, you would write A cos theta dB dt. Magnetic field has changed, A cos theta constant. And likewise, if only area is changing, you could say B cos theta dA dt. These two are simple to understand, but in third one, when you say that A and B both are constant, both are not changing, only this theta is changing, cos theta differentiated will be, it's given over here. You will take separately all the changes, and d phi dt becomes B cos theta dA dt. Then A cos theta dB dt. And then A B sin theta d theta dt. Cos theta has a differentiation sin theta, but along with minus sign. Now, whenever the flux changes, we have studied about change in flux because the entire base of this chapter is change in flux only. When flux changes, what happens? We are going to study in this chapter. Faraday's laws will clarify the whole thing. There are two laws. First is, whenever the flux changes with any circuit, EMF is automatically induced in it. This whole process is called electromagnetic induction, and if the circuit is closed or the coil is closed, induced current will start flowing in it. Second law says induced EMF is directly proportional to rate of change in flux, d phi dt. This could be written as minus N d phi dt. N is the number of turns in the coil, and this minus sign indicates that whatever the EMF is induced in this process, that is always against this change in flux process. This is second law. You see, N phi is known as flux linkage, where phi is the flux associated with one turn of the coil and N is overall number of turns in the coil. Now let's find what is the amount of induced charge in the process. You see, E is N d phi dt. You want to find induced current. For that you need V by R, Ohm's law, or the definition of current itself. So that way you get here N upon R d phi dt. This is induced current because you have divided EMF by resistance. If you multiply this current with the time, I dt, that becomes the charge, and that is minus n upon r d phi. This is the value of induced charge, you might say, and the important aspect of this equation is that this is independent of time. The charge induced in the process is not depending on the time. That's given over here, n upon r delta phi. Now, in order to find the current density, you see, you could write here current density as I upon A. This is going to be n upon r A d phi dt. We have taken the help of this equation I divided by A. Here also we have put A in the denominator. This is current density, and this becomes minus n upon r A. You see this d phi. Phi is B into A, so it could be written as A dB dt. A gets cancelled, and finally you have n upon r dB dt. This is the current density in terms of rate of change in magnetic field.